you hit 18 minutes, I'm going to pop in and tell you to start wrapping it up. All right, guys. And have y'all done your audio checks and everybody good?
Yep.
Okay.
Yes, ma'am.
All right. Y'all can take it away.
All right. Hey, everyone. Our design project is
Before we
PDOS.
start,
Oh.
Alex,
Okay.
hold on. Sorry.
Okay.
Before we start, I wanted to do the webcam thing that we did last time, where everyone turns off their webcams to draw attention to the speaker. We liked that last time, and we'd like to do it again. So.
Okay.
Okay.
We'll do that.
All right. Thank you.
Thanks, Liam.
Thank you, Alex.
Alrighty, y'all ready? Okay, I'll just go ahead
Yep,
and
we're
start.
ready.
Hey, everyone.
Okay.
Our design project is PDOS. It stands for Power Distribution Optimization System, and it's going to be an added feature on residential building management systems. My name is Alex Kane. I'm the Team and Battery Management System Lead, and I'm an electrical engineering student from Coldwater, Mississippi.
My name is Liam Nelson. I'm the Generation and Simulation Lead. I'm an electrical engineering student from Huntsville, Alabama.
My name is Noah Morrison. I'm the microcontroller lead. I'm an electrical engineering student. I'm from Madison, Mississippi.
My name is Christopher Jones. I'm the source switching and API lead. I'm a computer engineering student from South Haven, Mississippi.
My name is Thomas Fry. I'm the user interface lead, and I'm a computer engineering student from Jackson, Mississippi. And our team advisor is Dr. Jumbo Zhao. He's an assistant professor at Mississippi State University from the Electrical and Computer Engineering Department.
So today we're going to take you through how PDOS addresses the problems in the market, our design constraints, our approach, the hardware and software subsystems, and some of the progress we made so far.
Is everything okay?
Yeah. Sorry, I had really bad connection issues there. I'm back. Sorry about that. So I will be discussing the problem and solution portion. For our problem, there are no available products on the market that optimize and manage the use of generation resources. And what this causes is homeowners to not be prepared for power outages and forces them to purchase grid power at high prices. The solution to this problem is PDOS, and PDOS will allow the homeowner to integrate their building into their generation and optimize its usage. What this will do is this will increase homeowner preparedness for severe weather events, and it will reduce grid power usage at peak pricing times.
Okay, so I'm going to talk about some of our design constraints for PDOS. First off is our technical constraints. And the first one there is the power supply. Our power supply is used to ensure that the 9 volts that we are getting from the wall is stepped up to 12 volts DC in order to properly supply the battery. Next up is the battery life. That is to ensure that our battery does not go below 25% capacity in order to make sure that the battery does not degrade over time. Next is the forecast data and grid pricing data. These two are online APIs that are downloaded, that have their data downloaded from their respective websites to our system. And they both contain weather data and grid pricing data that will be that the system will accommodate for automatically, depending on what the data holds. Next is the solar panel inverter. That is a 120 volt AC inverter that can help the voltage fluctuation to where it'll only be within plus or minus 10% of the actual voltage gain from the solar panel. Next is surge protection, and that is where the PDOS will allow it to make sure that the circuit will not go get disconnected from in case of a power surge. And lastly is the power output switching, and that is to maintain the fact that the optimal power supply is determined automatically and is switched to accordingly. Next up are the practical constraints. First off is the economic type, the first one, utility cost. And PDOS is cost efficient with how it utilizes cheaper methods of supplying power through solar and a battery. Next is a visual type with the power switching indicator. PDOS will use 3 LED lights to show that what power source is currently being supplied from. Next is environmental type with renewable power, and that PDOS is energy efficient with how it utilizes power sources, and it'll be more beneficial to the environment for not applying grid power too much. Next is the quality of said components that make up PDOS, and that is to make sure that it does not get destroyed through power outages or any kind of inclement weather. And lastly is the safety, and we are going to have a protective enclosure around the central unit for PDOS, so that way it will be protected from the elements. Last off for our constraints is the engineering standards. First is the IEEE 802.11 standard, and that standard defines the wireless networking protocol for the Wi-Fi interfacing microcontroller that we're currently using. And next is the IEEE 2030.5 standard, and that is for our inverter in order to make sure that our inverter is configured the right way for the specific outputs that we are saying it's outputting. Lastly is the JSON API standard, and that is to make sure, and that is to confirm that we are using a client server transmission from the HTTP in order to send to and send data from between each component for the APIs.
Okay, so I'm going to take us through some of the approach and hardware overview. So we're going to start with the PDOS system overview. The Arduino is going to be the heart of PDOS. It's going to have 3 subsystems connected to it, one being the battery management system, which will have an LCD screen connected to the Arduino, which will display the state of charge and ampere readings. The second subsystem will be the Node MCU, which will allow the Arduino to go online and gather grid pricing data from the OpenEI API and gather temperature and forecast data from the Open Weather API. And then the last subsystem will be the Energy Plus, which will simulate solar production data and load data, and we'll transfer that to an SD card reader, which will allow the Arduino to translate that data. And now we're going to go over some of the hardware overview. We're going to talk about power, microcontrollers, and battery management system. So here's the current draw and power consumption for all of PDOS's components. The Arduino is going to serve as a main power distributor. The Arduino is going to take in 5 volts from the wall, and it's going to supply voltage to the Node MCU, LCD screen, and the micro SD card reader. The battery management system is going to have its own power supply of 9 volts from the wall, and we're going to step up that voltage to 12 volts using the Elysium boost converter, and that will be the maximum input voltage that PDOS will handle. With all these components, the total average current draw will be 25.2 amps, and the total average power consumption will be 436 watts. Now we're going to talk about some of the microcontrollers we considered for PDOS. We decided to go with the Arduino Mega 2560 solely because it's 54 input and output pins. PDOS requires at least 20 input-output pins because of all of its subsystems and devices connected to it. And the Arduino Uno and Raspberry Pi did not meet those requirements. Now, unfortunately, the Arduino Mega did not have a wireless communicator, so we had to go with another microcontroller, which we chose the ESP12E Node MCU for its wireless transceiver. We started with the ESP01, but it deemed unreliable and did not communicate with the Arduino very well. So now we're going to talk about the microcontroller connection between the Node MCU and Arduino. The Node MCU will connect to the Arduino through its ground and VCC pins, and they'll also be integrated between each other using the read and write pins. With this connection, the Node MCU will connect to the APIs through Wi-Fi and parse the data and convert that data into a readable format, which is the JSON format. And with our Node MCU doing that, the Arduino will read the data from the Node MCU, And it'll use the data for the generation and source switching algorithms, and it'll send control signals to the battery management system.
The battery management system is split into two subsystems, the charging and discharging subsystems. The charging subsystem consists of a 9-volt power supply that runs through a boost converter to step up the voltage to match the 12-volt battery. It also consists of a current sensor that will relay the current change through Arduino so the current and charging status can be displayed on the LCD screen. The charging subsystem also features a relay that's going to protect the battery by disconnecting the circuit when high current or high voltage are detected. Now, the discharging subsystem features a discharging unit and a cutoff switch. The cutoff switch detects and relays when the battery has only 25% charge remaining, and the Arduino activates the switch so the battery can never discharge below 25%. The lifespan of most lithium batteries is dramatically reduced by constantly depleting the battery of charge. So by stopping the battery from discharging below 25%, it ensures there is no damage to the battery and allows the battery to last to its intended life cycle. So because we care about safety, we chose a lithium iron phosphate battery over a lithium ion battery because they are newer battery types that's much safer to handle. We also chose the eco-worthy battery because it meets our 12-volt output requirement and our power requirement. Most residential solar batteries have a capacity of 10 kilowatt hours, so our 240-watt battery allows us to run our simulations at 2.4% size of the actual solar battery. And if you look at our table, you see there are two converters highlighted. The first is a step-down converter, and the second is a step-up converter. The step-down converter is used to test our battery management system to ensure it's working properly. So we're going to be using a small 3.7-volt lithium-ion battery, so the power supply has to be stepped down to meet the demand. Once we know our system is working, we're going to replace a small lithium-ion battery with our eco-worthy battery and use the boost step-up converter so the 9-volt power supply can match the 12 volts the battery needs. And again, we care about safety, so we didn't want to line up a bunch of resistors and draw current from the battery, possibly making it too dangerous for us to handle or even causing a fire. So we opted for the hide-up discharging unit because it meets our power requirements for the battery and also has built-in safety features such as overcurrent and surge protection and a fan that dissipates heat away from the circuit. This way, when we're discharging the battery, we're doing it in a safe and controlled manner.
Hey guys, I'm going to be going over our software overview. First, we have Energy Plus, which will be used to simulate the data, and then we have our algorithms, which will take that data and then do stuff with it, and then we have our user interface, which will take the stuff that's done with that data and output it onto a screen. First, we have Energy Plus. We used Energy Plus to simulate the data that we were not able to produce due to cost constraints. Energy Plus was created by the Department of Energy and uses verifiable data to simulate home energy consumption and solar production data. This data will be output in 10-minute increments in the summer and winter, and this will allow us to get diverse data from each season. This will record in total 144 data points over two 24-hour periods. And then all of this data will be pulled from the simulation into a CSV file, which will then be placed on an SD card, and then the algorithms will be able to react to that data accordingly. For our generation, the PDOS algorithm uses solar, battery, and grid power, and then decides amongst these generation sources to decide which one is used based on several factors. For solar radiance, this input represents the solar that would be generated from typical rooftop solar. The simulated Energy Plus data first is the input into the algorithm, and then the algorithm takes this data and updates it based on weather, simulation, temperature, and forecast data. All of these points are then used as efficiency multipliers and subtractors to produce the true solar output. And then, as I mentioned earlier in the Energy Plus slide, this will be output in 10-minute intervals. Next, we have grid pricing. Grid pricing represents the grid power that will be used in our project. The biggest factor to determine for this bucket of power is the grid price demand profile. TVA, which is a generation company that generates power to use in our area, has pricing tiers to calculate electricity cost. These pricing tiers include super peak power, which represents the most expensive option, peak power, off-peak power, and super off-peak power, which represents the cheapest option. And then we have inclement weather mode. Forecast data is taken from the Open Weather API, and then this will alert the system if severe weather is detected. It will alert the system by placing an identifier on the battery, which will then close off the battery as a power source until the start of the weather event.
So the source switching algorithm is really at the heart of what we're trying to accomplish with PDOS. As of now, it runs every 10 minutes in correlation with the Energy Plus simulation data. Here, we see a top-level diagram that shows the algorithm in its entirety. We have two main branches for solar and battery power, and then a third smaller branch for grid power. The rectangles represent functions that exist as part of the source switching algorithm, while the diamonds represent conditions to be met. These branches eventually culminate in two power slots being filled, a priority queue that uses the optimal source automatically. When the slots are decided, their combined output is checked against the load demand to verify that PDOS is working. Over the next few slides, we'll take a look at each branch and see the conditions that have to be satisfied for the power slots to be filled. We'll begin with solar. Solar is always going to fill our first power slot if it's functioning. We determine that by checking if its output meets a 50-watt threshold. This number represents the average power output for a solar panel at sunset, which is the last usable moment for the panels to generate energy. We feel that this threshold can also adequately represent when weather conditions prevent solar panels from functioning properly. Next, we check if the solar output can meet the demand. If it does, then we run the battery charging algorithm with the load difference. If demand isn't met, or solar cannot meet its output threshold, we check on the battery. With the battery, we're looking for two main criteria. Is the battery above 25% charge, and is there severe weather? If charge is accurate and there's no severe weather, then the battery will be placed in a slot. If solar occupies slot 1, then battery will occupy slot 2. If it doesn't, then the battery will occupy slot 1. The load demand is then checked against slot 1, and if it's sufficient, slot 2 is left empty. If it's not, the power grid will supplement whatever is left of the load. So in practice, the power grid is going to be used almost exclusively to supplement solar and battery energy. If solar and battery don't meet demand, grid is used as a supplemental source. If solar and battery cannot be used at all, then the grid is used exclusively. Power from the grid will always meet the full demand of the home. And finally, the battery charging algorithm starts by reading the current and voltage characteristics of the battery to determine power and instantaneous current supply ratio. Once the charging level of the battery is determined, the Arduino sends a control signal to the battery management system to begin charging. Once battery charging is enabled, the Arduino periodically checks the charge level of the battery to determine if that control signal should remain enabled or be turned off. And then here are the microcontroller libraries that we'll be using. These are software libraries used by the Arduino and Node MCU, programmed using the Arduino IDE. We're using 3 Arduino core libraries and then 3 open source libraries.
Okay, so for the user interface, we are the
Thomas,
main goal of that.
Thomas, you have about 2 minutes to wrap up.
All right. So for our user interface, our main goal is to have the data that was parsed through the algorithms transferred over to another server host. That could be any computer, but for example, we're using a Raspberry Pi 3, and that will generate its own web page that will view the results of from the algorithms and give you the data. And our URL will be generated in order for you to navigate it through any browser, and it'll feature stuff such as the weather, the grid power price, battery state of charge, and the current sources that are being used by the 2 slots. So for our progress so far, we have the microcontroller parts completed. We have the Energy Plus model done. We have the API data pulled from the websites. We are currently working on the battery management system, coding the algorithms, putting that Energy Plus data onto an SD card, and we're currently coding the web page.
So the reason PDOS was created was to be resilient. We wanted homeowners to be able to outlast a storm with emergency power. be environmentally friendly by focusing on primarily using solar and battery power, and by being grid supportive and cost effective by not using grid power during peak times. Thank you. Do you have any questions?
First of all, questions from audience. The safety bear team, do you have questions for PDOS guys?
So will this just act as like a power monitoring system for people's houses, or how will it, be used?
So, Liam, do you want to take that or should I?
Yeah, I can take it. So yeah, that's a good question. So what this does is this will be this can be input onto any home that has battery storage, solar panels on the roof, and then obviously a grid power connection. And if you have all those three items, then PDOS will then be able to slot into that and then manage those three source types, if that answers your question.
Yes, so this will basically make your house be more efficient by switching between the power sources to give you the best efficiency overall.
Exactly.
Great, cool.
Any more questions? If you all do not have questions, you still have some technical issues. I don't know, is it the team's problem or your computer problem? What is that?
Yeah. Yesterday we were practicing, and I think the school Wi-Fi had a blurb of issues just a second ago because I completely lost connection, and that never happened until today. So I think that's just luck. It's not on our side. So.
Okay.
Yeah.
Liam, okay. Your problem statement and the solution were very brief. Okay, so you need to highlight your problem and also highlight your solution. So you're doing a lot. So you need to highlight your solution and the problem statement. Okay, not like it's very, I mean, I felt very brief, very crisp. And I don't know, from Fry, did I hear that you've been telling that 9 volts from the wall? Was it from the wall or 9 volts from where?
It's not. It's sort of pulling 9 volts. Just
from the wall. How come 9 volts we get it from the wall? I mean, I don't know.
it's gonna be through like a regular DC source, just a regular D source that has DC on it, and it'll be stepped up to 12 volts in order for the battery to get supplied.
Yeah, but I mean, I don't know.
Alex, do you want to step in here?
I mean, it's just a wall plug that outputs 9 volts with 0.6 amps, and we're just stepping up to meet the battery for 12 volts. So we're connecting our battery management system to a breadboard and the Arduino, so the Arduino breadboard can't take 12 volts at 2 amps, or it's just going to heat up and melt or whatever. So we're using a smaller voltage and stepping it up so that our breadboard and our Arduino can handle that voltage.
Yeah, I'm sorry I didn't make that clear.
But it's just a wall plug that converts the AC to a 9 volt DC with 0.6.
Yeah, that's what. Okay, you need to say that. Okay, you have a converter there because the wall gives 120 volts AC. So you need to convert it to 9 volts, and then you step up or step down. So that is, I mean, you've been saying that, okay, 9 volts from the wall, 9 volts from the wall. Okay, come on. No, I mean, it's not 9 volts from the wall. Okay, so you have a converter in between, AC to DC converter. So you did that couple of times. And also, Fry, I still feel that you need more practice because you've been saying, okay, for example, like the grid API, the Energy Plus API. Okay, they both give energy data, and they both don't give, right? I mean, each gives, one gives weather data and one gives the energy data.
Yes, ma'am.
So while talking, I still feel that you need, more rehearsal kind of a thing. Okay. So you need to practice more. And also, okay, I don't know, did I miss it? I want to see some engineering standards on the solar panel or and grid, maybe.
We had inverter standards that it had to meet, but the problem with having solar panel and grid standards is if we're to tie into the point of PDOS is to tie into an existing system, right? So if we set solar panel standards, then I don't think that's necessarily a constraint, because as long as the solar panels are outputting something, and the inverter can take it and then output the correct power quality that we want, then we don't care what the panels are doing, as long as the power from the inverter is what we want it to be. And we did have a standard specifying inverter output quality.
For the inverter, yeah, that is important. Yeah, the inverter standard. Okay, yeah, okay, I agree with your explanation. Yeah, that's it. But you need to highlight the problem and the solution for sure. Yeah, that's all from me. Good presentation, and just these technical problems, and also some more practice, okay, from you guys. Miss Nordin?
Yeah, guys. So Liam, I did notice your connection issues as well, and that could just be Teams just dropping out on you a little bit. Teams will sometimes act up, so that could have just been an isolated Teams event. Thomas, I did notice that you tripped a little bit over your tongue. I thought you went through the constraints pretty well. It was just kind of a little bit of that tongue tripping, which might be an indicator of nerves, Thomas. So if you can try to relax a little bit, that might help with that problem. Noah and Alex, especially Alex. Alex, I thought your delivery was very smooth, maybe too smooth. Have you got a script over there, Alex?
I got some words up, but I don't have like my script right now. Because I didn't put a lot on the slide, so I just put up some extra words so I could see just go where I needed to go.
Okay. It sounded to me that there's a way your voice, that your cadence, basically, your speaking cadence changes when you're reading versus presenting. And I think you were reading too much, Alex. And I think probably you have some text up there. And then the danger with having text available to you is the temptation that you will read it because it's just right there. So I think I hear you reading a little bit too much, Alex. I want you for the final presentation at the end of the semester to lose the text and speak a little bit more extemporaneously, which means you've practiced, you know what you're going to say, but you don't have it's kind of scripted out for you to read off of. And so I would just say that's true for all of you guys. Make sure that you're not scripting out what you're going to say. It was very smooth. Like I said, almost suspiciously smooth, where I started watching your eyes to see if you were reading. And I think at times some of you were. I don't mean to just pick on Alex. I think I saw other people's eyes moving around too. So guys, make sure that you get that. I want you to work on that issue for the final presentation. So no scripts, no reading, just extemporaneous presenting. All right.
So, Miss, I have a comment on that. So I was reading off the slide. Should we not do that, or should we just have something memorized and we stare straight at the camera, or can we read off the slide?
You shouldn't really just be reading to us off your slides. And again, I would advise you not to have enough text on your slides that you can really read it to us, Liam. So I would say, guys, make sure that you have your important keywords on your slides, but not enough text that you can start reading. And then also, you don't want to memorize what you're going to say, because if you forget, then you're kind of dead in the water. So you don't want to try to memorize a script either, but just know your
Practice.
content well enough that you can just speak about it pretty
Yeah, your
confidently.
content was good, Liam. Okay, the problem statement solution, the content was good. Okay, it wasn't a lot. Only thing is you were just reading that one line. Okay, so that's what. Okay, so what I wanted was you explain more on the problem. Okay, take each point and explain.
Gotcha. I can do
Okay.
that.
Yeah.
Yep.
So similarly, highlight your solution. So don't read those lines. I mean, I
Gotcha.
think the content was fine, but you need to explain more. That's the problem.
Gotcha. That sounds good. Thank you.
Yep, guys. But I mean, I agree. I thought the content was good from my side anyway. But yeah, I need y'all to lose the scripts. Okay. All right, guys. Well, we gotta jet to the next meeting.
Yeah. Good job, guys. Just practice. Okay.
Thank you.
Okay.
Thank you all.
Thank you.
Bye bye.